Hello, everyone. Good afternoon. Thanks for joining our talk today. I'm Stuart Nguyen. I'm from Lenovo.
This is JQ from Cloudflare.
Oh, thank you. Hello, I'm Xiaoming Shen. I'm with Cloudflare. I'm a hardware systems engineer.
So today we'll talk about Project Argos, which is a DC-SCM 2.0 design implementation. We'll also cover as far as what we've contributed back to the OCP community. So what is Project Argos? Project Argos is a set of design specs based on the DC-SCM 2.0 base spec. In addition to the hardware spec we've already shared, we've also have contributed back to the community design collateral such as schematics, board files, BOMs, stack-ups, 3D, etc. Project Argos is a collaboration effort between Cloudflare and Lenovo and will be deployed in the next generation edge servers in Cloudflare data centers. As far as objectives for Project Argos, what you'll find is they will pretty much be in line with the OCP DC-SCM initiatives. Having a modular line allows the decoupling of the HPM and the SCM and provides many key benefits. On the HPM side, by having it decoupled, we're able to spin HPM with new CPU generation to generation, as well as other CPU architectures. Another key benefit of that is the HPM now becomes a more simpler exercise where the development cycle is reduced, which in turn means more efficient time to market. On the SCM side, having the SCM decoupled, we're able to be able to use the same module across many different platforms. And similar to the HPM, these would be able you're able to upgrade the SCM architecture with minimal impact to the HPM. Another key benefit is data centers now can have their customized system management and security designs, typically localized on the BMC on the SCM and segregated from the HPM. From the firmware perspective, our hope is to be able to support a unified OpenBMC across vendors. By having a closely unified hardware, we give it a better chance to be able to support a unified firmware. Although we do understand from vendor to vendor that there will be customizations that will be managed and hopefully minimized. Another key benefit is that we've been able to see is the cost reduction of the server, mainly in the PCB. With the SCM separate, we were able to use a less costly PCB material since most of the high-speed signals are on the HPM side. And another cost benefit would be being able to optimally panelize the PCB where we reduce the unused panel space, thus reducing the server cost. As far as overview is what Project Argos is, and Xiaoming and JQ would cover more in detail on some of these points, but it is based on the revision 2.0, version 1.0 spec. It's a single node configuration HPM versus the multi-node. It is implemented in the horizontal external form factor, so uses the coplanar straddle mount mechanical connections. At the heart of the SCM is AST 2600 BMC, and paired with the OpenBMC firmware would provide a rich set of features like remote server management, security, as well as control. For our R2 solution, we are using the ASC 1060, which provides the secure firmware authentication, recovery, firmware update capabilities for the BMC and BIOS. And to tie it all together, we use the Lattice CPLD, mainly used for the power sequencing and reset logic, and do support a variety of I/O interfaces, interconnecting the different components on the HPM and the SCM. With that, I'll hand it to Xiaomin.
Thanks, Stuart. For the next few slides, I'll give an overview of the Project Argus DCSCM block diagram and DCSI connector pin definition. As Stuart has introduced earlier, on Project Argus DCSCM, we use the 8-speed AST2600 BMC. The hardware root of trust service is AST1060 for the dual 64 megabyte BIOS ROM and a dual 128 megabyte BMC ROM. Another key component is the Lattice MatchXO 3D CPLD. We have a separate TPM module that can be connected to the DCSCM through the TPM connector. There will be another slide later to talk about the I/O panel. The Project Argus DCSCI pin assignment is fully compliant with the OCP DCSCI 2.0 version 1.0 pin definition for single node applications. I'll go into the details of the DCSI pin assignment. We reserved the PCIe by 4 Gen 5 interface. If needed, this interface can be connected to a PCIe endpoint device on DCSCM, for example, an SSD. There are two sets of USB 2 signals. Both of them are initiated by the HPM. The first one is connected to the USB Type-A connector on the front I/O panel. The second one is connected to the BMC. We assign a power button signal on the DCSCI. It allows us to have a second power button on the HPM for applications when the DCSCM is placed at the rear of the chassis. The LTPI and the SGPIO interfaces both provide communication between the DCSCM CPLD and the HPM CPLD. For the SGPIO interface, we use the alternate pin function. The SPI interface is initiated by the BMC. It provides communication to the HPM CPLD. The JTAG interface is also initiated by the BMC. It allows programming of the CPLD and FPGA devices on HPM, and in addition to FPGA and CPLD on PCIe cards. Okay, next we have two 100 megahertz clocks for PCIe. Both of them are provided by the HPM, and there are two PCIe by 1 interfaces. The first one connects to the BMC as the endpoint. It supports features such as video and MCTP over PCIe VDM. The second PCIe by 1 interface is connected to BMC as the endpoint, as the root complex, sorry. It can be connected to management endpoint devices on the HPM. We have two sets of UART signals connected to the BMC. On the DCSCM, we've reserved a header for the UART signals for debugging. Both eSPI and QSPI interfaces are initiated by the CPU. The eSPI interface provides communication to the BMC, and the QSPI provides communication to the BIOS ROM via hardware root of trust. Next, we have the I2C, I3C, GPIO, and miscellaneous signals, such as the 3.3 volt for the HPM through and the 3 volt battery power, and signals for power sequencing. The intrusion detection signal is active low. It is asserted when the HPM detects that the chassis cover is opened. Okay, we reserved a set of PECI signals for Intel-based HPMs. And last but not least, one set of NCSI signals for the NIC on the HPM. The next two slides give a summary of the pin assignments that we just talked about. Okay, there are two present detection pins on the DCSCI. Present 1 is pulled down to ground. Present 0 is connected to the active low enabled pin of the eFuse with a pull-up. When the DCSCM is fully seated, the eFuse becomes enabled and delivers 12 volt power from the power supply unit to the DCSCM. Based on the OCP DCSCM 2.0 base spec, the eFuse is optional, but having this eFuse provides protection over current events. The power budget for our Project Argus DCSCM is 19.8 watt. Okay, interoperability. Interoperability is our ultimate goal, transitioning from a traditional server motherboard design to a HPM plus DCSCM design. We are currently working with our ODMs and OEMs to ensure that we can have interoperability between DCSCMs from different suppliers. When we started designing our next generation edge servers earlier this year, we provided the Project Argus DCSCM to our ODMs and OEMs. They created designs following the Project Argus pin assignment, used the same key components as defined on the spec, and they also follow the same pin assignments for these key components. Doing this reduced design deviations and incompatibility. This is our first step towards achieving interoperability. For the next step of interoperability, we would experiment with new security solutions and our new management solutions. The new design will still use the same DCSI pin assignment to maintain interoperability. The differences on the hardware component interface will be managed in the firmware. Next, I'll pass on to JQ to talk about mechanical.
Thank you, Xiaomin. I'll walk through some of the mechanical designs that we use in Project Argus. For if we have not said it enough, it fully complies to the DCSCM 2.0 base spec. We use a horizontal EFF slots, uses a straddle mount connector, coplanar to the HPM. It uses a DCI card edge connector interface compliant to the SFF TA1002 spec. It also houses a removable TPM module that is fixed with a tamper-proof screw. It can be mounted at either the front end or right end of the HPM, depending on your server design. It adheres to the OCP chassis bay opening requirement and provides sufficient contact surface for EMI solutions. The front I/O panel contains all the typical I/Os that majority of server customers use today. It has the 1 GB BMC management RJ45 port. It has the USB port that is used specifically for UART COM. It also has a mini display port, USB 2.0 that is connected directly to HPM for keyboard, mouse, etc. It also has buttons and LEDs, power buttons, as well as the embedded LED, UID button, and an embedded UID LED, as well as a system status LED. So nothing very unique here, typical and adhere to what server design engineers typically have in their server design. In the DCSCM-based spec, there is also provision to include an internal lock mechanism. For Cloudflare as a security company, we want to make sure that the DCSCM install that may contain keys and secure information are physically secure in the server. So we asked our vendors to take a look and introduce the lock mechanism to physically secure the module inside the system enclosure to prevent easy removal, either accidental or intentional, by site operators without opening the chassis. So every removal of DCSM will trigger intrusion detection warning on our end. It is implemented using a tray rail as shown in the figure to the right and the bottom. Next, we'll talk a little bit about the firmware that we use on top of the DCSCM implementation. We developed a OpenBMC image to work with the DCSCM Project Argus DCSCM. It is built on top of the OpenBMC that is open source today. It definitely includes some of the vendor-specific or implementation-specific changes that needs to be added to make the system work. We also have the hardware root of trust firmware. It is built based on ASPEED open source Zephyr SDK. And we are working with ASPEED in implementing the specific root of trust model that we would like. All of the firmware is written in-house using open source as a baseline, and we do plan to contribute them when the development finish. HPM through for DCSCM, the DCM-based spec do have a provision for this as well, in addition to the common header area, broad info area, and a product info area that we have today. There is a DCSCM multi-record area that needs to be included, and it specify or have information of the mated DCSCM card or module. So we have, like Stuart had mentioned earlier in the presentation, we contributed the block diagrams, including block diagram for a SPI, I2C, UART, LTPI, PCB stackup, board placement, DCSCM schematic, PFL, DCSCI pin definition, power sequence, as well as the bill of materials. For firmware side of things, we also wrote a minimum bootable device tree requirement for in cases when the firmware has not fully developed and you want to test it on the existing HPM, at least the server needs to boot. So there's a minimum bootable device tree requirement there. Mechanical drawing is also included in the contribution. In terms of call to action, Argus design spec is published on OCP contribution portal. We ask our vendors if you are designing a server for us, for current generation and future generation, to make sure that you include Project Argus DCSCM 2.0 into your design. We will also make sure that in our future generation of servers, we continue to comply to the latest DCSCM spec, whether that's 2.1 or future. And if you have any feedback and input, these are all email, and we welcome your feedback. With that, that's the end. Any questions?
So in one of the earlier slides, you mentioned that on the PCB, the cost would be cheaper than comparing, traditionally just having in one set. What percentage from your experience could we expect that cost saving?
I don't think I have the number on top of my head, but I can just sort of say where the savings come from. When you have the entire motherboard design, including the BMC as well as the CPU, DDR and everything, the layers that needs to be to fulfill all requirements on the on the HPM side also impact your BMC portion of the board. By decoupling, then the BMC portion of the board do not need to scale accordingly to the CPU, DDR, or PCIe 5 requirements. So the majority of savings is from that end. I don't have a percentage on top of my head.
Thank you.
I have something to add to that. We don't have the exact data for this generation yet, but I remember on DCSM 1.0, I think Microsoft worked with WeWing on the DCSM module, and they did mention, I remember if I remember correctly, it's over 10% of cost saving. Yeah, because we shrink the motherboard to a smaller size. It becomes easier to panelize. It's you can make it a square shape, and you use on the motherboard you have to use ultra low loss PCB material, which is really an overkill for the DCSM module. So that's where the cost saving come from.
All right, with no other questions, thank you very much.
Thank you.
Thank you. Thanks all.
Thank you.